Ever wondered how a string of words can transform into a comprehensible thought, or how a physical quantity can convert into a digital signal? The secret lies in the magic of encoders and decoders, the unsung heroes of information processing in various fields. Imagine a world of neural networks, where encoders and decoders play a vital role. Picture an encoder in natural language processing or NLP. This encoder is a component of sequence-to-sequence models like the transformer architecture. It takes on the task of processing input sequences, say words or tokens, and morphs them into a fixed-length representation, often referred to as a context vector. This context vector is like a treasure chest, containing precious information about the input sequence, ready and waiting for the next stage of processing. Now,
Have you ever pondered the significance and impact of transformers in the field of natural language processing? If so, you're in for a treat. Today, we dive into the intriguing world of transformers, the groundbreaking models that are revolutionizing the realm of natural language processing. First off, what exactly are transformers? In essence, they are models that have been breaking multiple NLP records and are used in a variety of applications, including machine language translation, conversational chatbots, and even powering better search engines. Transformers have outperformed previous models such as recurrent neural networks, GRUs, and LSTMs. They are the focus of popular models like BERT, GPT, and GPT-2. But the real question is, how do they work? To understand transformers, we need to first comprehend the attention mechanism, the very concept that enables transformers to have an extremely long-term memory. A transformer model can attend, or focus, on all previous tokens that have been generated. For instance, while writing a short sci-fi novel with a generative transformer, as the model generates the text word by word, it can focus on words that are relevant to the generated word. This ability to know what words to attend to is all learned during training through backpropagation. Recurrent neural networks, RNN, also have the capability to look at previous inputs. However, the attention mechanism doesn't suffer from short-term memory. RNNs have a shorter window to reference from, so when the story gets longer, RNNs can't access words generated earlier in the sequence. This is true even for gated recurrent units, GRUs, and long short-term memory, LSTMs, networks, although they do have a longer window to reference from. The attention mechanism, on the other hand, given enough compute resources, has an infinite window to reference from, thereby capable of using the entire context of the story while generating the text. The prowess of the attention mechanism was demonstrated in the paper, Attention is All You Need, where the authors introduced a new novel neural network called the Transformers, which is an attention-based encoder-decoder type architecture. On a high level, the encoder maps an input sequence into an abstract continuous representation that holds all the learned information of that input. The decoder then takes that continuous representation and step by step generates a single output while also being fed the previous output. To summarize, transformers have revolutionized the field of natural language processing by pushing the state-of-the-art and breaking multiple NLP records. The attention mechanism is the key to their success, allowing them to have a long-term memory and focus on relevant words as they generate text. This model has proven to be superior to previous models like RNNs, GRUs, and LSTMs, making transformers a vital tool